the talk as short as possible since you guys must be very hungry.
We have 3 dimensions in
so
more components, maybe more.
Okay. This is another one of my talk. I first show you that with our experimental system of ultra-cold atoms, how we do the quantum simulation of a strongly correlated system. Then with the super exchange interaction drive, we just studied the quantum mechanism. Later on, I showed that also based on the super exchange interaction that we go to the regime of the counterflow superfluidity, where we observe signatures of the counterflow superfluidity. And we know that for the strongly correlated many-body system, since we cannot do an analytical solution as the perturbation is really strong, so we'd better do the exact diagonalization of the Hamiltonian. That way, when the system is large enough, it's not possible to do it with classical computers. Maybe we need to have an alternative way to do the quantum way, the quantum so-called quantum computation with some digital circuits or the analog one. Today I show you that we manipulate ultra-cold atoms to do the quantum simulation with particles trapped in optical lattice. And there we need to manipulate the many particles in a single particle level. So this is a typical model of the Hubbard model that we have in the lattice of the atoms, the tunneling in the neighboring sites and the on-site interaction, also the chemical potential different positions. So if we tune these knobs, for example, we study the computation of the tunneling and the on-site interaction. We will show you that the superfluid and the insulator transition in the computation of the T and U here there are some theoretical papers, and in 2002, this group achieved the transition along this direction, the insulator and the superfluidity. On here, the chemical potential, actually we have quite a few lobes for different filling numbers. And if we tune more that the onset interaction is much larger than the tunneling, we have for more than one species of the atoms, we have the spin model, which is called the super exchange. So there, I should mention that from Anatoly and Boris and some other guys, they proposed that if we engineer the super exchange, that we can study quite a few spin models. If we go furthermore, we just introduce some spin dependency. There we can surprise this leading order of the super exchange. We go to an even higher order of the fourth order, maybe to the study some topological models. There we have some experimental result on this model in some plaquettes. So we can also tune more of the interaction among the atoms for using Feshbach resonance or Rydberg grassing, and also with cavity enhancement for enhancing the interaction among the spins. So if you look at the spin model, we compare these two components, Bosse-Haber model, with the normal Bosse-Haber model here. There we tune the computation of the tunneling and onset interaction. We'll have the phase transition from the superfluidity to the insulator. This we can observe that in the momentum space that the phase coherence will be destroyed. We tune much more to that direction with much higher U. But here, the two component, both Haber model here, we have each component tunneling, onset interaction, and there is another term emerged that this is the interspecies interaction, which is different from, might be different from the intra-species interaction, and there will be a difference of the interaction here. Based on that, we tune the onset interaction of that one, and also the difference between the two species. That way, there is a phase transition from a Mott insulator, we call this spin Mott, and there all the atoms are just fixed on their own sides. We tune gradually to that direction. We'll show you that this is the difference between the interspecies and the intraspecies. Slightly, there's an imbalance between them. We will see that this is a superfluid state in the correlated space of the spins instead of the single particles. And this has been predicted somehow quite a long ago, like 20 years ago. And there, if we straightforwardly, we just study this numerically, we use a small system, maybe a few sites. We do the exact declination. We look at the occupation of the number. We will see that in the Mott insulator, in each side we have, for filling one, we have a single atom here. There's no fluctuation with the number of the atoms in the sites. And if we go to the superfluid state, we have in their fluctuation of occupations, we will see that the occupation could be 0, 1, 2, or 3. There is a Poisson distribution in the lattice size. If we go to the two-component one, we have the spins on each side. We have two spins. We have spin up, and spin down here. If we put the system in the so-called spin Mott phase, there we have the number for each of them. There's no fluctuation. In each side, we have spin up, just a single one, and spin down, a single one. We have together, we make a renormalization of the number of the atoms. We have here, there's no fluctuation of the number of atoms. But if you look at single component there, we will see that actually there is fluctuation of the occupation for the spin up. It changes. We tune the system to the counter superfluid phase. However, the statistics here is quite different from the single component superfluidity. You can see that for the order parameters of either of them, they are somehow, you do not have superfluidity for either component, but together in the correlated base, you have really the order parameter is non-zero. So this is a model of we will study in our experiment. So our experimental setup is a typical in the quantum optics lab. We have the vacuum lasers and electronics, and later on you will see below this the sense chamber of the vacuum. We have this is a section of that vacuum. We have the actual atoms which are trapped in the lasers. We just have below here a microscope. You can see the actual atoms individually. They're somewhere here with some numerical procedure. We just can identify any one of the atoms. So we have quite a lot of lasers for manipulating the actual atoms here. This is a single layer. We make imaging of them. We have a single set resolution of the single atoms, and we can also tailor the pattern of the atoms by the light shade here. You see that we can address a single line of the atoms or any of them with a programmable pattern of the light here. For example, we just choose a single one-dimensional tube here. We can count also the number of the atoms for example, of a 1D system, before the imaging, we just let the atoms expand around the orthogonal direction, and later on we count again. Here there are 4 atoms. In that one, there are 3 or 2 of them. So we have the resolution of the number of the atoms, also the spin. We can later on show you that we have the capability of identifying the spins. So as yesterday or a few days ago, some of the speakers showed that with the atoms, the electrons in metal there, the Fermi energy compared to the critical temperature. I mean, this is they have different orders of difference, but here for the ultra-cold atoms, as we know that the mass of the atoms is really heavy, so the critical temperature somehow compare with what it can achieve. The Fermi temperature, there's the final temperature we can achieve that's like 0.1 or maybe 0.05 of the temperature. Here we develop a technique for manipulating the entropy of a cloud of atoms as a reservoir and mod insulator, which is got protected. There we just develop a cooling technique there for having a really low temperature. Like what I can show you here, we have the atoms. This is the cartoon illustration. We have atomic fluid here. We just gradually increasing our trap depths there, and with a staggered potential, the deeper and the shallower, they just exchange entropy of the particle, and later on we have the higher entropy part will be blown away by a laser. Later on we have a mod insulator with exactly no defects here. We achieve a temperature like 1 nanokelvin of the system, and there we can, with this platform, we just study the super exchange driving quantum mechanism. For example, quite a few years ago, in these 2 groups, they use fermionic atoms in a one-dimensional system or in a plane. They show that with the driving of the super exchange of fermionic atoms, they finally achieve the ground state either for the one-dimensional system or for the 2D plane. They get the antiferromagnetic ground state. So we show you that actually in the 2-component bosonic system, if we tune here elegantly that the super exchange among the different species, we can tune with the local trap potential that create our super exchange with different signs. Like it could be positive or negative, and there we follow our potential curve that we can tune the system from the most beginning as a new order of the spins of bosonic spins, and there the ground state could be antiferromagnetic state as well. If we can engineer the super exchange interaction for tuning these potentials locally. So this is one of an example that we can tune the antiferromagnetic ground state of bosonic atoms, and we can also put the atoms like 2 bosonic spins in a same site there, and due to the here the interaction here, this is much larger than the tunneling, and we just have finally these 2 atoms either could be with the same spins or different species. They just form a composite boson with spin 1 as these are some virtual process with super exchange. We can study the spin 1 Heisenberg model, and there we showed in the experiment, we just have these two species of spins, we merge them in the same site, and we study the spin 1 composite bosons, and we study the dynamics of these particles. We can identify the different spin species, at the same time the number of the atoms, and there we study the exchange of the spin 1 atoms in superlattice. We observe that there is a bosonic enhancement of the occupation of the number of the atoms there. So with this sort of technique and the platform there, we just study here the two component, both Haber model with spin half system, and there we tune the system with the interaction much larger than the tunneling. We have in case there is an imbalance in between the intraspecies and the interspecies interaction, we have a spin mod phase, which means they just fix at their own sites for each of these two species. While if we tune these interactions comparatively with the same strength, and there the system will be driven to the counter superfluid phase, which is correlated to a XY ferromagnet. And there we just take image of the system, we count the statistics of the number occupation for each of the species. And so you can see that there we have from the beginning, we have the system, maybe this is a single species system, and there we just have the hair entropy part. We can make spin flip and blow them away, and we have such a system of every 4 rows. We have these atoms. You can also see here there's a defect, and we just make spin flip. We merge them together. So we have a system of a one-dimensional system. However, with 6 sides in each one, we have the 2 spins. We just drive the system along the phase transition here adiabatically. From that one, we have the counter superfluid state, and we make detection. Before the detection, we do the similar trick again. We shift the spin of that one, the spin up atoms, and keep this one frozen by a laser light. So there we divide them again and count the number of the atoms, and finally we could count how many atoms which are in the spin up and how many atoms in the spin down on each side. And with that one, and finally we go that cycle. We can. This is what we observe finally for the system in the spin mod, and each of the species for the spin up atoms we have here. There's no this is the occupation of 0, 1, 2. All the time, each species of the spin just sit at their own sites. There's no number fluctuation of the atoms, and together we put them together at the same. Yes, we have on each side 2 atoms. On the other way around, if we tune the system to the counter superfluid state, we will see that actually we have the number fluctuation of each of the species. But if we put them together, it just seems like we push one of the component, the other one, we just drag the other one. But they have a conservation at that site. We have the occupation of almost 2. That's like close to 2. There's a renormalization. We have the 2 atoms here, but the fluctuation here for the occupation of 1 or 3, this is even smaller than the single component. This is evidence that if we make statistics of the covariance of the between the two components. In this regime, we have very low correlation that here in between the two species is a much higher correlation between these two species. And so if you make statistics over the noise correlation, which means we just release the 1D tube and we let them fly, the two species of the atom just fly in that tube. The momentum, the information of the momentum will be redistributed to the position, and there we make a statistic over different momentum and different species, and there we show that at the beginning in the spin mode there's no correlation here. You can see that between the two species, but the same species you have intrinsically. Here's the background of at the quasi momentum of 2 pi, you have the correlation between them. And later on, if we go to the counter superfluid state here, and this one, the correlation between the two species emerges. You can see that, and we verify this in our experiment. You can see at the most beginning, this origin curve was very low comparatively at the beginning, but after we tune the system to the counter superfluid state, we have this correlation between the two species, as I show here. This one actually, the color was reversed. Actually, this one was enhanced. If we tune the system from this is the experimental data, we tune the system from the spin mode into the counter superfluid state. So, and later on, we just study further the long range off diagonal spin correlations. We show that actually we just only have 6 sides, and there we derive the correlation length like almost for the full system. And here, as the amplitude is a little lower than the theoretical prediction, as we have a finite temperature, which makes here the imperfection of the correlation. And also we study the spin structure factor, which indicating the so-called X-ray ferromagnetic is emerging during the adiabatic transfer. And with all of those observables, we show that finally these are very concrete evidence for showing the emergence of the counter superfluidity. So finally, I show you that we have a system with very low temperature, like around 1 nanokelvin, and they're almost a perfect one-dimensional system. We can also tune the number of the atoms, like this filling one-dimensional system. We can also put in 2 atoms at the same time, and so there we have the microscope. We can detect the 2 different species, and we can study the bosonic antiferromagnetic state, and also we form the composite spin 1 bosons with 2 bosonic spins. So here we show you the experimental evidence that we have the counterflow superfluidity. Neither of the 2 species are superfluidity by themselves, but together they form in the correlated space. They are really the counterflow superfluidity. And further, I will show you that we may, with that quantum simulator, to study the 2-dimensional counterflow superfluidity at finite temperature, and also spin 1 Heisenberg model support a Haldane phase. We may detect these topological phases at the same time, and you see that actually ago, they proposed quite a very nice ideas on study the Borromean counterflow superfluidity with higher components, but maybe this is really tough for our experimentalists to achieve with much more components. And this is our team. We Zhen-Wei Pan, myself, as the PI of the team. We have the postdocs and the doctoral students. At the same time, we have theoretical support from my colleague Eugene. He has quite a few discussions, maybe with some of you guys here. And before I go to the end, actually, I show you, I draw attention to another emerging application of what we are doing with the super exchange-based quantum simulation here. You see that this is a U1 lattice gauge theory Hamiltonian. We have here the matter-gauge interaction. These are the matters, and we also have the matter field. For sure, in principle, we have another term of the gauge field itself. But here we have. I show you that we have the system, the actual code atom. If we tune the lattice, we have a linear potential along that way, and you will see that the occupation of the atom, like you have a single atom here. Here's here. This is a vacuum. We have another atom here. If we apply here linear tilt, this one is on resonant with the occupation of that one. They are degenerate. We have 1, 0, 1 and 0, 2, 0, or the other two simultaneously. They just jump together to here. And this one between this term and that term, actually this is also at the amplitude of the super exchange. You see that here we have annihilation of one atom here, another one here. Together they jump into the same side, and this Hamiltonian somehow is the same with that one. We just make a map in between the U1 lattice gauge theory. This is some kind of quantum link model in between that one and the modified Bossa-Haber model. And here we study this one and that one. We just have application of our spin system to study the so-called lattice gauge theory. And with that one, if you are interested in that direction, I show you that we have done quite a few work already. We can study the 1D Schwinger model in a quite large system, more than 71 sides of the lattice. We simulate the matter field and the gauge links. We study the thermodynamics in such a system. We also simulate the so-called confinement physics with such a system, and also show the stream breaking and force vacuum. Even though this is a U1 gauge lattice gauge theory, and along that direction, we also have a quite nice progress. We have studied quite a few different gauge symmetry, the Z2 and U1 gauge. We're studying the confinement of the Schwinger model, and also we extend the system to a two-dimensional one. Maybe in long-term vision, we may study the gauge theory of non-abelian gauge field, or even to the SU3. Maybe we study what is happening of the dynamics in colliders with our actual code atom quantum simulator. And finally, this is our colleagues along that direction, which we have a application of the actual code atoms in the spin regime to that of the lattice gauge theory. And finally, I would like to thank you for your attention. Thank you.
Any questions? Yes, please.
Yeah, it's extremely exciting to see this progress. Just really exciting.
Yeah.
And what are like your prospects of going for particular for Counterflow? What are your prospects for going for larger systems in near future? to get more size. How difficult is it?
Yeah.